So I want to spend a whole movie talking about oxygen containing compounds. As I said earlier, the stronger infrared signals come from the polar bonds. And so from my perspective, given all of the other analytical tools that are available to today's chemists, infrared spectroscopy is really only useful when you have compounds that contain oxygen and nitrogen. Now, some of my colleagues would disagree with that, but pretty much unless you're a dedicated infrared spectral organic chemist, you're going to use infrared spectroscopy, but then you're also going to use mass spectrometry that we'll talk about next week, and particularly NMR spectroscopy that we will talk about in 2 weeks. But anyway, here I've pulled out from the chart some appropriate bonds or frequencies that we might see for the bonds as we think about oxygen compounds. And I'm just going to compare suitable pairs of organic compounds. So let's start off comparing 1-propanol to propanal. In other words, the mild oxidation product of 1-propanol. So here's the spectrum of 1-propanol. Let's see what we can see. Well, starting off at the left at the higher wave numbers, there is that very, very, very diagnostic OH frequency, the OH stretch. Now I could talk about the CH stretch, but pretty much every organic compound is going to have that CH stretch there. So I'll leap all the way down here and I see some more nice strong bands here, right at around 1,000, a little bit higher than 1,000, and that is of course the CO bond right there as expected. So the two fun peaks that I see with propanol, the OH as we would expect and the CO that we would expect. About half the time when one's looking at an infrared spectrum, one is interested in what is there. But a lot of the time you're also interested in what is not there. And in particular, as you see more and more of these spectra, the first place your eyes will go to is this middle bit right around here. And you'll see, well, there's nothing right there. Well, what do I mean by that? Well, let's pull up, to get specific, the spectrum of propanal. Now in propanal, let's see what we don't have. Well, the first thing we don't have is a nice big OH peak there, because propanal doesn't have an OH. The oxygen's got the carbon-oxygen double bond. And indeed, that shows itself as what we do have, a very, very, very diagnostic peak, beautiful sharp peak here, just a little bit past 1700 reciprocal centimeters, and that is the carbon-oxygen double bond, and that is what is not present over here in the spectrum of propanol. Okay, propanol, nice OH, nice CO, no C double bond O. Propanal, no OH, a nice C double bond O, and notice up here, no nice strong CO single bond, because propanal doesn't have a CO single bond. Okay, so these two spectra here, really I don't need to go any further, although of course I will, because I love the sound of my own voice, but this really shows what it's all about. How do we look at compounds that contain oxygens and say what's there? OH, CO single bond, CO double bond, or what's not there? No CO double bond, no OH bond, no CO single bond. Staying with 1-propanol and now thinking about fully oxidizing it to propanoic acid, what can we see in propanoic acid? So here is the spectrum of propanoic acid, and you can see here we've got everything. There's this really yucky, wide, massive peak here that's centered around 3000. Well, that's the OH bond for acids. So you see the OH in acids, slightly lower frequencies than the OH associated with alcohols. And that's just associated with a little bit of the delocalization of electrons that you can get associated with the OH of alcohols. So we've got a beautiful OH peak. Continuing on down, we've got again a very diagnostic, beautiful peak, just about 1700, a little bit more, of the carbon-oxygen double bond. And then, of course, we also have in propanoic acid the carbon-oxygen single bond out here just about at 1000. Okay, so propan-1-ol, OH-CO, no C double bond O. Propanal, if you remember, all it had was the C double bond O. Carboxylic acid, now you've got the best of both worlds. You've got all of those important peaks to oxygen. And while we're on the subject of propanoic acid, just to really drive the point home, let's compare the spectrum of propanoic acid to the spectrum of one of its structural isomers, methyl acetate. If you look at the formula of these, they're exactly the same formulas. These are structural isomers, except of course notice what methyl acetate doesn't have, that propanoic acid does have. You can see that beautifully from the spectrum. There is the nice lack of OH there. Of course, it also has carbon-oxygen double bond in that beautiful position there. In this case, a little bit higher, up at about 1750 here, I would have said. Notice too, it's much sharper. Okay, the acid peaks tend to be much broader and yuckier, mainly, as I said, because of that electron delocalization that you can have within the acid that you don't have to the same extent, anywhere close to the same extent in esters or in, of course, the alcohols that we looked at. And just, of course, to wrap it up, a nice, beautiful CO single bond peak. So there we are, oxygen compounds really based around three potential peaks. Do you have OH? Do you have C double bond O? Do you have C single bond O? What you can't do, however, using infrared, is distinguish between compounds that don't have or do have significant differences in the groups. And just to close up here, let's look at 1-propanol against 2-propanol. Okay, they're different molecules, they're different isomers. They have different reactivities. When we oxidize this, we get aldehydes and carboxylic acids. When we oxidize this, we get a ketone. Okay, they're different compounds. But when you look at the infrared spectrum of 1-propanol versus 2-propanol, you got the OH peaks, you got the CO single bond peaks. You don't have the CO double bonds. Obviously, if I was to compare these spectrum, I can see other differences here that would enable me to distinguish 1-propanol from 2-propanol. But as far as just, hey, I've got this unknown compound, what's in there? It's not going to help you distinguish between these two alcohols. Mass spec will do a little bit of a better job. NMR will do a significantly better job.